for assignment 3. We're here to uncover the potential of our latest machine learning project aimed at predicting the obesity level. This technology allows for new possibilities, transforming how we approach complex challenges. I will walk you through a quick demo, showcasing our end-to-end pipeline, highlighting how we teach machines to make sense of data and assist us in making informed decisions. We will then reflect on our findings, discuss what worked well, and where we can improve. This critical evaluation is key to our growth and the advancement of our machine learning initiatives. To wrap up, I will underscore the broader impact of our work and its future implications. The dataset used for this project is retrieved from Kaggle, and the name of the dataset is called obesity levels. The purpose of this project is to predict the obesity level based on the given variables. The platform chosen is Microsoft Azure. Azure provides services such as compute, analytics, and storage. The components we use today are cloud storage, real-time analytics, and data transformation. Then we'll move to how pipeline was designed. First step is to select the raw data that retrieved from Kaggle. Second step is to clean data if necessary. Third data is to split data for train and test dataset based on for a given ratio. Fourth step is to train the dataset with a certain classifier. Then we'll score and evaluate the model with test datasets. Now we move to the part to showcase our demo using Microsoft Azure pipeline. The first step of our demo is to log into Azure Machine Learning. After logging to Azure AI, then you can move to the part of Azure Machine Learning Studio. This is the interface you will see when you successfully get there. Second step of our demo is to create a new machine learning project. We will create a new resource group. A resource group in Azure is a container that holds related resources for an Azure solution. It is used to group together various Azure resources so they can be managed as a single entity based on lifecycle and permissions. The name of the new resource group is called Obesity. Then the workspace called Obesity is successfully created. The workspace is designed to leverage generative AI for creating applications that interact with users in a conversational manner, utilizing the vast data resources and analytics capabilities of Azure Machine Learning. The prompt flow refers to a process or a tool within machine learning that facilitates the interaction between the AI and the user, handling the input prompts and generating the corresponding AI responses. Is a part of the broader set of tools for ordering machine learning models and applications within the Azure machine learning environment. Under the data section, the create button allows us to create a new data set with a name called obesity. The dataset is the CSV file downloaded from Kaggle with name obesity level. After clicking on the create button, first we have to select the type of the data with tabular form. The tabular form allows us to visualize whether there's any missing value from the Explore page. For our project, the dataset does not have any missing value, which saves the time for data cleaning. After select the dataset as tabular form, the columns of the dataset is shown as a preview in the schema step. For our project, we will select everything for the dataset creation. So after reviewing, the dataset is created with name obesity. After creating the dataset, we need to create the computer cluster. The virtual machine tier we selected as dedicated and CPU as virtual machine type. We set the computer name as computer, set the minimum number of nodes to 0, and the maximum number of nodes to 1. Then the computer cluster is successfully launched. After creating the dataset, we can move to the designer part to design our pipeline. You can hit the create a new pipeline feature with the plus sign, and this will lead to the next step. On the left side of the page, the data is now shown. We can drag the dataset to the right side. Now a box of dataset called obesity is shown on the right side. We selected all columns from the datasets since nearly every column of data is useful for increasing the accuracy of the model. We split the data into train and test dataset. The fraction of rows is selected to 0.8, which is 80% for training and 20% for testing. This fraction of rows would allow for avoid overfitting. The target column for this project is NoBStat, which is the target column in the dataset retrieved from Kaggle. This column provides the obesity level of participants and will be the target column for this project. After defining the target column for model training, we have decided to use logistic regression algorithm for predicting the obesity level. Then we'll use the score and evaluate model search on the left side. In Azure machine learning, you would use the scoring step after you train your model to access how it performs on a validation or test dataset. The output of this step is usually a set of predictions that can be compared against actual outcomes. The evaluation step typically follows the scoring step. You use these results from the score model step, the predicted values, and compare them to the true values to compute the evaluation metrics. These steps helps you understand the performance of your model and guides you in making any necessary improvements before deployment. Next step is setting up the environment for pipeline. The environment name is called Obesity Experiment, and the job display name is Obesity Pipeline. Step 5 is runtime setting. We first select the Azure Machine Learning Computer cluster as computer cluster, then complete the pipeline setting. Now the environment will be exited.
The completed pipeline. In this view, we see a successful run of our Azure ML pipeline featuring a multi-class logistic regression model trained on the obesity dataset. The data was split and used to train the model, which then underwent evaluation with the score model and the evaluate model step. Showing as key performance metrics, the green check marks indicate each phase went smoothly, and we now have a robust model trained and ready to action. Now let's go to the next step, understand the explanation from the train model. In Azure ML Studio, we are looking at the explanation sections on our train model. The left picture visualization shows aggregation feature importance, pinpointing weight and FCVC as top factors affecting prediction in our obesity dataset. The right-hand side chart displays our model's accuracy through the split of correct versus incorrect prediction. These insights are vital for refining our model and enhancing its prediction power. Next step, read metrics from evaluation model. Here we have the evaluate model metrics from our Azure ML pipeline, presenting us with crucial performance indicators. Our model scored around 0.77 for precision recall, signifying a reliable prediction rate. Overall accuracy sits at 70%, 77%, a solid starting point for our classification task. These figures are key for measuring model quality and guiding future enhancement. Now let's move to step 20, create inference pipeline. The left screenshot is zoomed in on a section of Azure ML pipeline inference, showing an option to create inference pipeline which include real-time inference pipeline and the batch inference pipeline. This indicates the point in the process where we can decide how the model will be consumed, whether it will process data in real time, which is commonly used for instant prediction, or in batches, which is suitable for processing large data set at once without the need for immediate feedback. The second screenshot shows a more complete Azure ML pipeline with a web service input and web service output, which are part of a real-time inference pipeline. The setup is used when the model is deployed as a web service, allowing it to receive input data through the web service, score the data using the trained model, and output the prediction. It is an end-to-end flow that takes a trained model and turns it into a consumable service, ready to integrate with applications for real-time prediction. In summary, these images depict the transition from training a machine learning model to preparing for operational use, demonstrating Azure ML's capability to support both batch and real-time inference workflows. This versatility is key to accommodating various application needs, from on-end prediction to large-scale data processing. Now let's set up the environment for real-time inference. We're getting to step 21. The left image shows us defining the basics of our pipeline job setup. We're naming our job associated to existing environment and adding a description plus any relevant tags for organization purpose. This is the initial configuration step that ensuring it correctly labeled and tractable with our Welder Azure ML workspace. In the right screenshot, we are setting up the compute environment for our pipeline job in Azure ML. Here we select the compute type and the specific Azure ML compute cluster, which is known for its balance of CPU and memory and is suitable for a variety of tasks. The green status indicates that it's ready to go, and we are to keep the community to failure, which means that pipeline will process even if the step encounters an error. It is useful for debugging and testing. Together, these actions are about preparing and configuring our ML pipeline environment, choosing the right compute resources, and detailing the model for clear identification and managing. After that, let's get into step 22. We set up the real-time endpoint. This screenshot shows the setup data for deploying a new real-time endpoint in Azure ML. We were intended to deploy the model as a web service on an Azure container instance, which provides a lightweight and cost-effective option for real-time model scoring. The setup process involves specifying a name for the endpoint, which is essential for identifying and managing the service when it's deployed. Choosing ACI suggests that our deployment is likely for low to medium traffic or for a development scenario. After deployment, the model will be wrapped as a web service that can receive data, run prediction, and return results in real time. Now let's see how our endpoint looks like. We are getting to step 23. In the first image, we are viewing the deployment setting for real-time endpoint in Azure Machine Learning. This setup process was where we give our endpoint a name and select the compute type, which is Azure Container Instance, ideal for quick deployment and lower scale prediction needs. The model is now wrapped and ready to serve prediction on demand and make secure with key-based authentication. The second image displays our endpoint listed in our Azure ML workspace. This overview is particularly useful for keeping track of deployed services. It shows that our real-time endpoint is set up and ready, linked to the Azure container instance for compute, which says it configured for handling prediction requests as they come in real time. Here, we can manage the endpoint, monitor its activity, and integrate further by deploying additional endpoints if needed. Together, this image underscores the completion of a phase in our ML operation, transition from model training and evaluation to make our model actionable and accessible for real-world predictions. As we have built the machine learning pipeline in Azure, we would like to share our reflections of our projects. The first is the experience in working on ML pipelines in Azure. The experience was enlightening. Azure ML is a robust platform that integrates various aspects of machine learning into a cohesive environment. This includes everything from initial data handling to model monitoring. One hand of the standout feature was Azure ML Studio's interface, which is remarkably user-friendly, providing drag-and-drop module alongside classic code-based environments. This allows us to efficiently manage datasets, environments, and deployments within a single pane of glass. However, the journey wasn't without its challenge. Navigating Azure's complex pricing structure and the resource management option require a steep learning curve. Setting up the right compute resource, understanding scalability option, and managing costs were particularly demanding without past deep cloud experience. Talking about intuitive and less intuitive activity. In terms of intuitivities, uploading data was more straightforward. Azure ML Studio interface for uploading and accessing data is user-friendly, making it easy to import data from various resources and the real dataset. On the other hand, configuring compute cluster and deciphering the best option for different tasks were less intuitive. The granularities in choices, while powerful, made it initially hard to select the optimal setup from our specific needs. Furthermore, while Azure does provide monitoring tools to track everything from cost to performance metrics, these tools weren't as accessible. They require custom setup and familiarity with Azure's monitoring philosophy, which could be a barrier for those not versed in cloud-native technologies. Talking about suggestions and enhancing MLOps functionality in Azure, we have several suggestions which would be beneficial. The first one is user-friendly resource management. Azure could simplify how resources are set up and managed. A more intuitive interface with recommendations for different user cases would help users efficiently select the manager and manage resources without needing extensive cloud knowledge. The second one is advanced monitoring integration. Incorporating more advanced monitoring tools directly into Azure ML Studio would provide users with immediate insight into their model's performance and operational metrics, all without leaving the platform. The second is proactive error management and resolution guidance. Enhancing Azure's errors messages with more actionable insight and direct troubleshooting support would vastly improve user experience. For example, when a deployment fails, the platform could offer tailored advice or automated troubleshooting steps. The fourth one, streamlined documentation and learning resources. Azure's documentation could be reorganized to provide cleaner learning paths tailored to different user levels and use cases. Interactive tutors and example projects could also be enhanced to better demonstrate best practices in real-world content. Last one, communication engagement support. Strengthen the communication support framework with more frequent interactive sessions, QA board monitored by either expert and the user group meeting apps would help foster a collaborative learning environment. As we wrap up our discussion on designing and deploying a ML pipeline in Azure, we would like to give some crucial takeaways to encapsulate the core lesson and the strategies we have explored today. The first one is comprehensive planning is absolutely crucial. This process goes beyond just understanding what you need. It's about aligning those needs with the right resources and manage costs effectively. Azure offers extensive tools and services, and knowing how to leverage those from the start can save both time and resources. Second, the effective use of tools provided by Azure, such as Azure ML Studio, can significantly simplify the complex ML lifecycle. This platform offers an integrated environment that supports everything from data preparation to model deployment and monitoring, making the management of these tasks far more straightforward. Regarding data management, remember the importance of secure, accessible, and well-prepared data. This foundational as the quality of accessibility of the data directly influence the performance and the scalability of the machine learning models. Continuous monitoring is another essential aspect. It ensures that the system not only runs smoothly, but also stays relevant and effective over time. Azure provides powerful monitoring tools to help track everything from performance to cost, enabling proactive maintenance and optimization. Last, let's remember that MLOps is an iterative process. This field of machine learning and the tools available are constantly evolving. Staying updated with the latest development and the continuous refining the approach are key to maintaining an efficient and effective pipeline. Now let's go to our conclusions section. We would like to take a moment to recap the journey we are undertaking today and highlight the crucial points that make Azure a powerful platform for our MLOps needs. Firstly, we explored how Azure provides an end-to-end integrated environment, from the initial stages of data ingestions to the complexity of the model deployment and the ongoing needs of monitoring. Azure Machine Learning Studio serves as a one-stop solution that caters to all phases of the machine learning lifecycle. We then discussed the scalability and the flexibility of Azure's infrastructure, whether it's using Kubernetes service in AKS for heavy duty, scalable model training, or use ACI for more sporadic demands. Others ensures that we have the flexibility to tailor our solution to the specific demand of our workload. One of the standout features we cover today is the powerful tooling provided by Azure, notably Azure ML Studio. Its user-friendly interface is accommodating for newcomers, while its deep and robust capability supports the needs of the even most experienced data scientist developer. We also emphasize the importance of proactive monitoring. Azure's comprehensive suite of monitoring tools not only help us keep our system running efficiently, but also enable us to quickly adapt and respond to performance bottlenecks or operational issues as they arise. Lastly, we recognize that the field of machine learning and the tools we use are continuously evolving. Staying updated with the latest offering and enhanced from others will ensure that we maintain a competitive edge and continue to improve our project. In conclusion, Azure ML stands out not only just as a tool, but as a partner in our journey towards building the robust, scalable, and efficient machine learning solutions. Thank you for your attention today.